So I wanted to make one point in the beginning, which I think you are in the final year, so I'm sure I have made this point earlier also in your class. So when I'm asking a question and I'm calling someone to give the answer, you should feel free to speak and give the answer. The answer is right or wrong is not very important, but that you are going to give an answer is very important for me. So please don't hesitate or say that okay, I don't have a clear answer or anything. Whatever you can think on the spot, I want you to think and give the answer. Is that fine? So keep don't hesitate or don't feel shy to speak or don't feel that someone will think bad of me or someone will think good of me. All these things you should not worry. So just keep speaking as you think that of course this online class is like that. You are alone in your house where you are attending. Nobody else is there around you. Maybe others are listening to you in the class, but that doesn't matter. So we will keep this as our smallest rule that we all follow. Okay, so in the whole of statistical mechanics, if you understand that there is one concept that is of great importance, and that is the concept of an ensemble. Okay. And we have talked about ensembles in great detail right in the beginning. But suppose if I ask you a question like, now tell me what is an ensemble? Suppose if I ask this question. Okay. So let me know. I will request someone to speak. Okay, so you can whomever I request you can speak, and then I will. Otherwise, if all of you either all of you speak together or none of you speak, then it is going to be kind of
The
lost.
sir, ensemble is like the possible outcomes and the probability of the outcomes.
What?
The possible outcomes and the probability of it occurring.
Arya, who spoke now?
Ashri, your things.
Revati. Okay. So say that again.
The possible solution or outcomes and the probability of it occurring.
Okay. So possible outcome and probability of outcome. Okay. Now, um, is there uh, is there any addition or a modification of this answer that any of you would like to give?
So
Sir,
Yes.
possible microstates and probability of the macrostates to occur.
Possible microstates and
Probability of the microstates to occur.
so you want to replace this outcomes by microstates.
Yes, sir.
Microstates and you want to say probability of
Probability of the microstates to occur.
microstates. Okay. Jace Johnson, do you have something to say?
sir, I was about to say the same, sir.
Okay. So any other thing?
Yes, sir. It's kind of collection of identical units, sir, or any replicas of the system.
Lakshana Shubhankar.
Uh,
Okay. Collection of identical units.
yes.
Identical units of
Or it's the replica of the actual system.
replica. Yes. Are these two statements same? Whatever you have written. That is the first two statements which Srivardhini and Devanjan have said, and what you said, are they same? Bharati Priya? Bharati?
Yes, sir.
Hi, Bharati Priya. You have anything to say, or do you agree to one of these things?
Sir, I couldn't hear you, sir.
Have you been hearing the discussion?
Sir, can you? Hello?
Can you hear me? Are you able to hear the discussion that is going on?
Sir,
No, you couldn't hear?
sir,
Bharati, are you able to hear? Okay, there seems to be some problem. Are others able to hear my voice?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
So probably Bharti has some difficulty. Okay, that is fine.
Sir, I would like to add, sir, to my answer.
Yeah, please.
So it's a large number of collection of large number of mental copies of identically macroscopically identically prepared systems,
Hmm.
but which are different microscopical.
Okay. So can you repeat? A large
It's a
number of
collection of large number of mental copies means identically prepared mental copies, macroscopically identically prepared, not microscopically.
identical macroscopically.
Yes, sir. And the accessible, we have to look at the accessible microstates and their possible probabilities.
Yeah, so identical macroscopically, but you also said something called mental copy.
Yes, sir. But it is not real actually.
Copies
It's like a thought experiment.
prefer
Microscopically. And we have to look at the different accessible microstates and their probabilities.
and problem. Okay. Surya,
Hi, sir.
Surya, what is your answer to this question? What is an ensemble?
Same answer, sir. Possible microstates with their respective possibilities.
Possible microstates with respective
Possibilities.
probabilities. You mean probabilities?
No, sir.
Okay. Shweta? Shweta, are you still attending classes from outdoor environment? Can you hear, Shweta? I think she has severe problem with connection. Is it raining in Pondicherry? That is what Rishivaran is saying. Lakshmi Sri? Lakshmi Sri? Sri Gugan?
Hello, sir.
Sri Gugan?
Hi, sir.
Yeah, tell me, Sri Gugan, do you have any?
Sir, look like a large amount of space something. It's a infinite, something of infinite.
Hmm.
In infinite, each one have should be possible, possibility.
Hmm.
That's maybe, you know.
Okay. Sunakar Sahu?
Yes, sir.
Yeah. Tell me,
All
Sunakar.
these statements means the same thing.
All these statements mean the same thing.
Yes, sir.
Okay. But anyway, so we can discuss whether they are all same or not. Abhijit,
Yes, sir.
are all the statements same?
Yes, sir. It's all of them are same, sir.
All of them are same. Okay. So then let me just try to understand. See, when you say that I have a system, okay, so we have a simple system like this. I have a system, and this system has got certain number of particles. Okay, this is our typical macroscopic system. Okay, so this number of particles are very high. They are of the order of 10 to the 25 in number. Okay. Now, when you say you have identical macroscopically but differ microscopically, what does that mean? That means you will label this system with something called a macro state. Okay, what is a macro state? It is some set of macroscopic properties. Okay, and this is like a thermodynamic state. Not limited to thermodynamic state, but it is like a thermodynamic state. Okay, so that should be same. that should be same, and they can differ microscopically. Microscopically means their positions can be different, their momenta can be different, their spins can be different, and if any other property they have, that can be different. Each particle can have different property, but when you try to find out a macroscopic property, that should remain the same. And that is perhaps what this identical macroscopically but differ microscopically means. But when we talk about this mental copies, Debanjan also said that it is not real, it is like a thought experiment. Okay, so is it like a thought experiment, or is it like they are not real systems?
So I think those are real, sir.
Sir, but at a time only one can exist.
Yeah. So essentially, what? But this language is not uncommon, because you see many textbooks use this language. So we have to understand what do they mean by this. They exist. So we have labeled this one for our convenience. We call something called a microstate. Microstate is essentially, if you have this kind of a system, you define all positions and momentum, you call this as a microstate. Okay. So now the point is that you can have distinct microstates corresponding to same macrostate. Okay, that is possible. Okay, so when you talk about now, why we should consider this one? Why we consider this one? Because let us say you have a system with a fixed value of energy, fixed value of volume, fixed value of number of particles. Now, let's say this is in equilibrium. Okay, suppose if the system is in equilibrium, then these things do not change. That is fixed. These things do not change. But what you observe is that there is a continuous motion of the particles. Okay, but constituent particles continuously change their position and momentum. That means this Q of P or Q bar P bar, this is not constant. This changes with time. Okay, so if you imagine some kind of a 6n dimensional phase space with Q bar here and P bar here. Now you start with a Q bar and P bar, a point in this phase space. Now this Q bar and P bar keeps changing as a function of time, and then it may trace some kind of a trajectory. Okay, so it may have some trajectory as time goes. I'm just drawing some trajectory. So this changes. That means at some point your microstate is here, at some other point it is here, and the microstate actually traces this orbit that I have drawn here. But this dynamics, okay, so this dynamics essentially, I mean the trajectory of particles is largely inaccessible. To us for observation. We will not be able to access the details of this trajectory or details of this dynamics. Okay, so now you can imagine that if there is no reason, suppose I have a particle in this volume, if I have no reason to believe that this particle confines to left half of this box, I would imagine that this particle will be everywhere in this box. Okay, in the process of in the process of microscopic dynamics, this particle will go from here to here to here. Every part of this volume it might visit, and so are the other particles. So I can say that now I am going to say that there is one microstate in which the particle is at this top left corner, and there is another microstate in which it is in the middle. There is another microstate in which it is in the left bottom corner, and so on. Now I can have different microstates. Okay, imagine. Why I have to imagine? Because I don't have an access to observe. But it does not mean that this is a thought experiment, because in reality the particles are going everywhere. So all this the mental copies, whatever we are saying, are being realized in reality. If they are not realized, now whatever you calculate by using this picture of different mental copies will not come out to be same as what you observe experimentally, isn't it? So it is real in as much as the particles are changing their microscopic dynamics such that every microstate is visited or every microstate is accessed. However, since we don't have a direct observational accessibility to us, we say that, okay, these are the possible configurations in which your system can be found. Okay, now the possible configurations can be enlisted only by their consistency to the macroscopic conditions. Okay, I cannot say a microstate whose energy is not E, then it is not a part of this system at all. I cannot take a microstate where some of the particles are outside this box, then that is not a part of this system at all. I cannot take a microstate whose number of particles are more than n or less than n, which is not a part of this system. So consistency with the macrostate tells you the possible microstates. Okay. Now the possible microstates, once you enlist, then depending on the conditions, depending on the environmental conditions and the interaction of our system with the environment, nature of interaction of our system with the environment, these possible microstates will acquire their probabilities, their chances of occurring. Okay. Now, just to give you an example, suppose you have a system. Let's say these are n particles in a box, and you know, particle in a box has got let us take quantum mechanics. Let's say that you have particle in a box n1, n2, n3 has an energy like this: h bar square pi square times n1 square plus n2 square plus n3 square divided by twice mv to the power 2 by 3. So this is your energy levels of particle in a box. Now let us say that this system where there are so many particles in the box, this is of course single particle states. If they are not interacting, that is fine. Now let's say that you keep this in contact with a heat bath. Okay, so this is heat, this is a bath, and let's say this bath is at 0 Kelvin. Okay, for an argument's sake, let's say bath is at 0 Kelvin. Now what happens because of the interaction, and let's say that the interaction is such that these walls are energy transparent. That means energy can be exchanged between the system and the bath. And the temperature of the bath being 0 Kelvin, the bath cannot give any energy to the system. Only system can give energy to the bath. Continuously, system will transfer energy to the bath, and bath by definition will be very large compared to the system, and bath's temperature is not going to increase because of the energy transferred from the system, and therefore system will give all its energy to the bath, and then it will equilibrate to a state where the ground state E1, 1 will have a probability of 1, and then all other states will have probability 0. Okay, other states. All other states will have a probability 0. So why I am giving this example is the probabilities that these microstates will have are not just the property of the system, but it is the property of the system plus surroundings. So depending on what kind of surroundings the system is interacting with, and depending on the nature of interaction, you will have different probabilities for the different microstates. Now the statement that we have made is something like this, which is very so as I told you that you have microscopic dynamics, and that is given by, usually you can deal with this classical mechanics or quantum mechanics. Okay, and then you have a state called Q bar, P bar, which we called in this new theory a microstate. Otherwise, in classical mechanics, this is simply called the state, microstate. And then you have macroscopic level, and then you have a macro state. Okay, so for example, in this case, you may say that your macro state is fixed value of energy, volume, number of particles, and then you have to go from here to here. Okay, so this is essentially what you do in thermodynamics. It's a thermodynamic state. Now, statistical mechanics is a bridging formulation. Starting from microscopic dynamics, you have to derive thermodynamic properties, laws, and equations, etc. And this is where you have the concept of ensemble. Ensemble is very central because this ensemble is what is going to connect these two things. Okay, so this ensemble by definition is written as you have different microstates and their respective probabilities. That is what is an ensemble. And this different microstates are consistent with the macrostate. Different microstates are consistent with the macrostates. And different microstates they have different probabilities. different microstates have got different probabilities. Okay, so that way your aim of going from microscopic dynamics to macroscopic dynamics is achieved by defining an ensemble, and this ensemble is in general is considered as the state of a system. Macrostate is the state of the system in thermodynamics, microstate is the state of the system in classical mechanics, and the state of the system in statistical mechanics is called an ensemble. And mathematically, this ensemble is given by a probability distribution function, rho of q bar p bar, and it can change with time. Okay, so this is the q. So now from this understanding, you can look at all the things that you have read, and then see how to understand the statement in the correct perspective. So there was a question in the examination that I said you have three coins tossed, and I think I have asked. There are some three different things I have asked. Let me see if I can get that question. So I have three statements. One statement is the HT, then statements. So TTT with probability 1/8, all kinds show up head. So I have A, H, T, T, B, one of the coins. So head and C, T, T, T with probability 1/8. And which is an answer. Okay, so now you can so now how do we answer this question?
So I think A and D are microstates.
A and D are microstates.
And B is a macrostate. And C is the ensemble.
Okay. Any other?
Sir, A can also be said as a macrostate because there are other possibilities also with this. Like we can take THT and TTH.
Yeah,
Those
but
are
it's not given, no. When I
Yes.
say HTT, that means the first coin is head, second coin is T, third coin is T. That's all.
Yes, sir.
So the other possibility you are imagining. Okay, I am
Yes,
not
sir.
giving that. So this is simply a microstate.
Yes, sir.
okay, because every coin state is defined here. So this is simply a microstate. Now, one of the coins shows up H. This has all these possibilities that you are listing. That is HTT, THT, and TTH. Because I did not say which one is showing up. One of them is showing up. So all these possibilities are there. Okay, so this is the macro. Okay, so now I have also given a microstate and then its probability. Okay, I've given a microstate and a probability. So this is the statement of what an ensemble is. Ensemble should have the statement of microstates and its probability. Okay.
Sir, but if we assume that all microstates are equiprobable, then it's an ensemble. But other microstates are not equiprobable, then it won't be an ensemble. Sir.
Okay.
1/8, I mean, equiprobable. We have
Correct.
not mentioned that.
Correct. So, okay. So let us look at. Okay, let us come back to this question. But let's see what is this. All are H.
So we can take as microstate.
All are H is a microstate. I can also call it a macrostate because there is only one microstate corresponding to this macrostate. Correct.
Yes,
So
sir.
now let us look at all possible microstates. All possible microstates are all heads, head, tail, head, tail, head, head, and head, head, tail, tail, head, 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 tail, head, and head, head, tail, and tail, tail, tail. Okay. Now, since this is just a two possible system, that means two possibilities, namely head or tail. Okay. If I fix the number of one possibility, the number of other possibilities is already fixed because it is 3 minus that, right? So I can have my macro states labeled as 0 heads, 1 head, 2 heads, and 3 heads. These are different macro states. Okay, different possible macro states corresponding to this macro state. And 1 head, 0 heads. 1 head corresponds to this macro state. So this is 2 heads. Okay, 1 head. Oh, I think I have written this wrong.
So that
HT, HTT, and TH. Okay. So this is 1 head. Okay, this is 0 head. This is 1 head. And this is 2 heads. And this is 3 heads. So corresponding to each macro state, there are certain number of microstates. It may so happen that some macrostates have only one microstate. In this case, macrostate and microstates are same. Now, the point which Arshad is making is that if all of them are equally probable, okay, if all of them are equally probable, then each one will have a probability of 1 by 8, 1 by 8, 1 by 8. Okay? 1 by 8, 1 by 8, 1 by 8, 1 by 8. Now, the point is that when you say that you have TTT with 1 by 8, now this in itself is not an ensemble because it is a part of this bigger ensemble. Because it is also important that when you say you have an ensemble, you have to you have to say that the total probability should be equal to 1. So when this becomes an ensemble, when I say it is TTT with probability 1, if I say, then that becomes an ensemble. When I say TTT with probability 1 by 8, it is not an ensemble because it is only a part of this ensemble. So when you say TTT with probability 1 by 8, okay, and I have not given that they are equally probable, but whatever is the probability, you know that it is a part of the ensemble. And in this ensemble, you have only one microstate corresponding to this this macro state. Okay, so you can categorize this also under macro state. Okay, so it is not an ensemble. So what is that we have to understand here is that if you want something to be categorized as an ensemble, I must give you microstates, I must give their probabilities, and their probabilities must add to 1. If the probabilities are not adding to 1, that means I am not stating the probability. For example, I can say, so let us try to write this one. So let us say I have HTT and THT and TTH with the probability 1 by 3, with the probability 1 by 3, with the probability 1 by 3. Okay, so if I give this statement, this is an ensemble. Okay, this is essentially an ensemble corresponding to which state? So one head, this microstate. Corresponding with this microstate, I have this set of microstates, and these are respective probabilities. All of them are adding to 1. In that case, we can say it is an ensemble. Okay, because I must give for a given macrostate all possible microstates that are probable. So I would say that if I TTT with the probability 1, if I say, then that qualifies to be an ensemble. If I say TTT with the probability 1 by 8, that means what? There is a possibility that the coins will have other microstates. And how the coin will have other microstates, it depends on the interaction of the coins with the environment and all that. But whatever it is not the total statement of the state of a statistical mechanical system. Okay, so that is so is there any question?
Sir, I have a question, but it is not related to this. Sir, can we say randomness is our inability to accommodate all the variables, or are there truly random processes?
See, the point is that so you are asking a question whether this randomness that we are because of which we are introducing statistics or probability, whatever.
Sir, is there a question to me?
No, I'm trying to ask your question only. I'm trying to write down your question. So I think you are asking, is this inherent or is it due to our ignorance? Is that the question?
Yes, sir.
Okay. Okay. So before I answer or tell my answer, if there are any other comments on this, any of you would like to give your opinion on this?
So I think it's inherent because of second law of thermodynamics.
Okay. Okay, so that is one opinion.
Sir, both are true. They are inherent also, and we are also, there is some kind of ignorance from our side also.
Okay. So is there some proportion that it is largely inherent or largely ignorance? When we say we have two things, do we have any more information on how proportionate are they? Are they 50% inherent, 50% ignorance?
Sir, like when we deal with probabilities in quantum mechanics, we basically deal with probabilities, and there this concept of probability is not because of our ignorance; it's because of the intrinsic nature of the process. So it's
Okay.
inherent, sir. I think.
Yeah, but we are not now talking about quantum mechanics. I think Jace Johnson's question is with respect to statistical mechanics.
Yes, sir, it is with respect to statistical mechanics.
So let us ask this question with respect to statistical mechanics. Okay, maybe I will ask a question which is the same question but slightly in a provocative language. Okay, so the question is, do we feel hot because of our ignorance? Now, why I am asking a question like this is because it is because of this randomness that as a property. So is this emergence of a property called temperature is connected to our ignorance, or it is intrinsic?
Emergence of temperature is intrinsic, sir.
Okay. So that means, can we now conclude that the randomness is also intrinsic, because it is because of the randomness that the temperature emerges?
I don't know. Can we say so, sir?
I'm just trying to pose this question such that you can think aloud. For that, I first want you to think about this statement: the temperature emerges as a property out of randomness. Is that clear, or is there a doubt?
So temperature is basically kinetic energy of the particles, right? So it's randomized. That's why the temperature.
Correct. If there is no if there is no randomization, suppose let's say you have n particles, all of them are flying in the same direction like a flock of birds, can we define temperature for that system? Like a disciplined set of soldiers, if all the particles are going in a single direction, is there a temperature for that system? Let's assume there is no randomness in their motion, but they have kinetic energy. Correct? But that kinetic energy is not going to give you temperature. However fast, they may be moving relativistically fast, but that is not going to give you temperature, right?
Sir,
Yes, sir.
when you talk about this temperature, it is for an equilibrium system.
Yes.
But sir, when the soldiers are moving in particular direction, is that an equilibrium one?
See, equilibrium is associated with a system and its surroundings. Right. So you can have, for example, let us look at this this expression. There is something called Maxwell distribution of velocities. Correct. So Maxwell distribution of velocities. Maxwell distribution of velocities. This is an equilibrium distribution, okay, for a gas. So that is given by, suppose if you have some velocity v, the distribution is simply given by some constant, which I will not bother to write what it is, exponential of minus half m v minus some v naught, the square, divided by some kb. Okay, correct. This is how it is as far as the distribution of velocities is concerned.
Yes, sir.
Now you can see that this v naught is some kind of a velocity which is like a directed velocity of all the particles. Okay, you say this is like some BC component. In the sense, all the particles have this velocity. You can make this 0, that means particles don't move. They only have random velocity. They don't have a directed velocity. Now this v minus v naught is what is the random component. This v is the total velocity of the particles. Among them, you have to remove this directed part. And that is what gives rise to the distribution of velocities. So this distribution of velocities is essentially without that drift part of the velocity or a directed component of the velocity. Okay, so that way there can be a directed component, but you can have a situation where the, so just to tell you how this can happen, suppose let's say that I have some kind of a chamber in which there are gas particles, and let's say that I'm dropping this gas particles as a free fall. This is our Earth. So if I'm falling, if this is falling, let's say m times g, there is some directed velocity of all these particles. Now, as an environment, if this entire region is fixed at some constant temperature T, I think the number of the temperature of the system does not change. We can consider throughout this fall, this system to be at same temperature and hence in equilibrium. But there is a V naught which is non-zero at this point, compared to this one is sitting on some laboratory in a rest condition where V naught is supposed to be 0. Okay, so in that sense, if there are particles which are just going in this direction, there is no random movement, then for this system, even though of course this whole system may be, so this system is going like this, then this system, we cannot define temperature. What is temperature here? Now the system, if it is in contact with some environment, and if the environment can interact with the system, transfer energy, then this will no longer continue to be in this motion. Just like we discussed with a similar system earlier when we talked about equilibration. Okay, so that is what I am trying to say. So the temperature emerges as a property just because of the random motion. Just because there is a random motion, and that is why you say that in kinetic theory, that you say that 3/2 kBT is not equal to half mv square. It is actually equal to half m average v square, and this average v square has to be calculated by this distribution. Okay, so you have to calculate this average v square by taking this distribution into account. So when you do that, this is average kinetic energy that is equal to 3/2 kT. We talked about this when we talked about laser cooling in the last class. So this is essentially the randomness. That is what gives rise to the temperature. So this is just to make some sense of what I have written here. But then we come to this statement that do we feel hot because of our ignorance?
So if we have one particle only, so in that case, we cannot define temperature. Because
Yeah,
we can, that is not random.
Yeah.
You can predict its motion. Yes,
Okay, so what are you going to make some point based on this?
No, sir. Just I was asking that if it is true.
Okay. So it is like suppose let's imagine that you have only a single particle. Okay, and let's say that you pump this particle inside this chamber in this direction. So now you assume that this particle will enter in this chamber, and then if you wait long enough time, then this particle would actually acquire velocity in all possible directions. The particle at some instant may be like this, at some instant maybe like this, at some instant maybe like this. This is what is called equilibration. Now, why should that happen? Because this chamber itself is maintained at some temperature T, and the chamber is maintained at some temperature T means that the walls of the chamber have got their atoms which are in thermal motion. So this particle will see this box as some kind of a corrugated surfaces like this. So when the particle comes, it comes here and it reflects, even though these are all elastic collisions, and there is a possibility that it reflects in all possible direction, and hence it will go over to this kind of way. So this is equilibration, and the equilibration is because of the temperature. So I can say at this point that the particle is in equilibrium with the system. Once this particle will have this, so in terms of time, suppose you try to find out velocity of the particle, so vi you calculate, and I is like at different times. Okay, at different times, because I don't have too many particles, I have only one particle at different times, and then I look at what is the distribution of these velocities. So distribution of these velocities, then you will see that the distribution will be same as the Maxwell distribution. So that means even in this case, you will have an equilibration. I can say this particle is at temperature T. That is because the environment or the box in which it is there is maintained at temperature T. Okay, so we can talk about the temperature of the particle in this sense. But suppose if you say that I have one particle in isolation, there is nothing it is interacting with, there is nothing it is colliding with, then we cannot define a temperature for that particle in whichever way it is moving. Okay, so I think one of the instructive example to look at this issue is, again, let us go back to this coin toss. Okay, so coin toss, we don't know the outcome. We don't know the outcome. Okay, and what is the reason for this? We don't know the outcome because so in this case, because we ignore a lot of details. We ignore a lot of details, such as the interaction of the coin with the air during its toss, etc. We may ignore many other things. And because we are ignoring this, we are not doing hydrodynamics of the toss of coin, we will not be able to say this. So this looks like this is essentially, so the randomness in coin toss is due to ignorance. Okay, one can actually do a detailed calculation and then say that we can predict what is going to be the outcome of the problem. Okay. So this is one level. Okay. Now let's look at, as Debanjan was pointing out, some kind of a quantum system. Okay, so let us say that I have, let's say I have a state 1 over root 3 times up z plus square root of 2 by 3 times down z. Okay, so let's say I have a spin half particle in this state. Okay, now let's say I have an oven in which these particles are prepared in this state, and a series of particles will come. And now I try to, okay, so let me not worry about. So let's say this is an experiment in which I can measure Sz. So when one particle is coming, so I measure Sz. What comes out is this reading. Okay, so this reading is +1 or -1 random. Okay, it is +1 or -1 random. We cannot predict this. Now we ask a question that is it also due to our ignorance? Now the answer seems to be at this level is not, because here I am able to say that I did not do these things. If I did these things, I can predict it. Now, here, what to do to get rid of this randomness is something that we do not know. Okay, so this appears to be intrinsic. Okay, appears to be intrinsic. There were a lot of attempts to say whether this is also because of ignorance, and such theories are called hidden variable theories. So one of the aim of hidden variable theories has been that okay, there are some variables which we do not know, but when we know them, then we will be able to predict these results. Okay, so here hidden variable theories have been an attempt to see if it is due to ignorance. Okay, but there is no success in terms of a fundamental or unified theory, fundamental theory where you can get a hidden variable theory such that quantum mechanics can be explained. So at this moment, it appears that this is an intrinsic randomness. That means we are not able to say that if you do these things, you can get rid of the randomness. Okay, so this is.
Sir, what about chaotic systems, sir? In that case, can we even write an ensemble?
Okay, so let's come. Okay, let us, anyway, since you mentioned it, let me just come to chaotic systems. So what happens in chaotic systems? Now, chaotic systems are like they are deterministic systems. Okay, so they are deterministic. Deterministic in nature. Okay, what does it mean? That means if you give, so if we give, let's say, an initial state, then x of t can be determined rather uniquely for all time. Okay, but suppose I start with suppose I look at x of t versus t. Okay, and let's say there is something called a stochastic system. Stochastic means a random system, like a Brownian motion, for example. Take a Brownian particle and then look at x of t, then the Brownian particle will have some kind of a trajectory. It's random. There is no, you will not be able to predict where this will go at the next time if you know the position at this time. Now, you can also say what happens if you take a deterministic system, deterministic but chaotic system. Okay. Now, the chaotic system also more or less looks very random. Okay, chaotic system also looks very random. So there is no, apparently it looks like there is no difference between a stochastic system and a chaotic system. So now the question is that whatever is appearing random, is it because of an underlying chaotic dynamics? So this question was very burning question, very important question in the late 90s and early 2000, those 20 years ago, and people have been trying to look at whether there is, that is, can we understand the dynamical origin of a stochastic nature of any system. For example, in Brownian motion, the stochasticity comes because of the collisions of the particles of the solvent molecules to the Brownian particle. And these collisions are random, these collisions are unbalanced in random direction, and as a result, this Brownian particle will execute randomly. In chaotic system, there is nothing like that. Chaotic system, everything is deterministic. That means you have a well-defined differential equations which you can solve, but there is something called non-linearity that plays a very important role. So the non-linearity in the equation will actually give rise to something called sensitive dependence on initial condition. That means normally if you have a regular dynamics, if you say that you give x of 0, okay, if you have x of 0, let's say you have x of t versus t, and let's say that this is whatever is regular dynamical system, like what we are using two-body problem, two-body problem, like Sun and Earth system, or Sun, Earth and Moon system, something like that. Let's say that I have given this as my initial condition, and then let's say that the system may exhibit some kind of a motion. Whatever is this motion, I am typically drawing something like this. Now, suppose if I say that I am going to start with a different initial condition. Let's say I start an initial condition somewhere here, let's say, then this is going to be somewhat closer to this. Okay, it will not be too much away from this. Okay, so if you make a small error in initial conditions, you will be within that error, you will be close to the trajectory that actual initial condition is supposed to be. Okay, so this is what happens if you have a regular system. On the other hand, if you have a chaotic system, then the situation is somewhat different because of the sensitivity to initial condition. Suppose you have some kind of a trajectory like this, then suppose if you have a different initial condition, okay, so let's say you have a different initial condition, so it actually tries to be very close to this up to some time. After that, it just becomes completely uncorrelated. Okay, so one of the important quantity that people who are interested in chaos will be interested to study is what is the time up to which that remains closed. Okay, so this is what is called a kind of a predictability time. Up to this time, up to time tau, you can predict. After that, you cannot predict. Okay, so this is somewhat proportional to something called largest Lyapunov exponent. There is something called Lyapunov exponent. Lyapunov is a Russian mathematician. So there is something called Lyapunov exponent. So some largest Lyapunov exponent, inverse of that one. So this time is related to that. So in the long run, you will have different the correlations are completely lost in this particular time. So even though you made a small mistake in giving initial conditions, but the final result is going to be something very different. So the famous the butterfly effect, which people call in a popular level, is that if a butterfly is flapping its wings here, and this kind of a event might have changed the initial condition in your weather modeling, and this small change in the initial condition may create a storm in a faraway place. That means Your weather modeling, weather is a global dynamical system, and a small change that may happen, just like a butterfly flapping its wings, can actually create a hurricane in a faraway place, because you can completely get a different result. So it's not that it's a small error, and these errors get multiplied in different ways, and you have this. This is what chaotic dynamics is. So here, the randomness, that apparent randomness, there is no randomness. So the apparent randomness that you see in the end result is of a dynamical origin. Okay, there is no randomness as such. There is no ignorance also. There is no intrinsic in a randomness also. It only deceptively random. It only appears as if it is random, but it is not random. There is a dynamical structure. There is a dynamical reason why this randomness appears, and all that is deterministic. But yet, this is very important, because many complicated dynamics will have this kind of a chaotic nature sometimes embedded in this. And if you have such a nonlinear system, then it is important, because when you are trying to make predictions in terms of dynamics, then it is important to check if it exhibits chaos. One of the practical systems where people study this chaos in the laboratory is sometimes chemical reactions where some nonlinearities are involved. Lasers, for example, I think in our department, Shiva Prakashan, there's a lot of work on chaotic dynamics of diode lasers. So laser dynamics. So when there is a feedback of a laser from an outside mirror to the cavity, there's going to be a lot of change in the phase and energy dynamics, and that has important. In fact, Shiva Prakasam had entered into this field because when he was doing PhD, the lasers stopped working. He was not working on this. In terms of analyzing why they stopped working, then he discovered that there is an intrinsic dynamical thing, and then that's how he entered into this field. And he did for a long time when he was abroad, interesting experiments. But after coming here, he turned to theory, and right now he is doing dynamical systems analysis of this laser dynamics. Okay, so that is the question of chaos. But now, what is the dynamical structure that the system picks up this kind of a random, apparently random behavior? That is a very interesting question. It is, in fact, my PhD was my PhD work was on trying to distinguish chaos from stochastic systems by looking at their final graph, because both the graphs look same, whether it is from a noisy system or whether it is from a I was attempting to distinguish chaos from noise by looking at the final data. That means how to understand the data and then say that this is from a deterministic system and this is from a stochastic system. So that is about chaos.
Sir, in that case, the noise will be random, right?
Noise will be random, yes.
Okay, sir.
Okay,
thank you,
so
sir.
now let's come to this statistical mechanics. So I think our question is still remaining, statistical mechanics. So the randomness in statistical mechanics. So now we have talked about three things: inherent, ignorance, or dynamic. So is it inherent, or is it ignorance, or is it dynamic? So this is what we have so far said, that this is inherent in quantum mechanics. This seems to be ignorance in coin toss, and this seems to be dynamical in chaos. Now there is another place where you have, interestingly, the random behavior comes in hydrodynamics, that is turbulence. Okay, turbulence. Turbulence is also a very complicated phenomena, and understanding turbulence dynamically was another great aim that chaos, when the theory of chaos, etc., have started. People wanted to understand, okay, we will now probably understand turbulence in terms of spatio-temporal chaos and so on, but it also did not succeed to that extent. In fact, chaos as such was showing some promise that it is going to finally explain statistical mechanics, but it didn't, and it has grown as a separate field of its own, and of course with a lot of applications of its own and so on. So let me also tell you there is another interesting proposal. The proposal is something like this. Suppose, let's say that I have some trajectory like this. Let's say x of t. Let me say that I have some two variables. Let's say y and x. Okay, so x of t and y of t. But I am plotting x versus y. T is implicit. Okay, so that means, let's say I have a very nice curve like this. Okay. So would you say this is deterministic because I am starting from here in a very nice way, I am going up to this? It seems to be deterministic. I can say it is deterministic because there is a unique curve and so on. But now let's say that I will only look at x coordinates. That means this is my x1, x2, x3, x4, and then x5 is again coming back, x6, then x7 is going back like this, coming back like this. So if you just look at only xi, only x coordinates, then it looks like it is going back and forth, or it is just varying randomly. Okay, so the question that is asked is, is randomness observed in a system? Is randomness observed in a system a consequence of ignoring a part, and probably a large part, of the whole system. Now, if the answer for this question is yes, then that means this ignorance theory is correct. That means we are now not considering all the variables, but only we are considering some variables. But other variables are ignored. But if you consider all of them, then there is no randomness. It is somewhat like hidden variables. We don't know hidden variables. If we know them, there is no randomness. Okay. So this question has a very interesting prominence, and many people attempted. But when we say that something is very successful theory, because for every problem, if I am able to identify, okay, if I am able to identify a bigger system, including the ones that I have ignored, and establish that because of my ignoring, this randomness is emerging, then it is fine. But there has not been much of a success with respect to this idea. But this idea is still being under consideration. So people try to ask a question: is it possible to design a bigger theory? Especially with respect to quantum mechanics, this question is gaining more importance. Okay, so now people understood what it means to ignore the system, mathematically what to do if you have to ignore. And now people are again coming back to this question of asking, can we ignore? Now you take a bigger system and ignore a part of the system, and then see what are the statistical properties of the remaining system that you have. So such attempts are now gaining more importance to see whether this statistically, at least statistical mechanics, is it because of the ignorance? So largely it is believed that whether you are able to establish or not, we don't have a way of establishing, but because it is not very easy to establish, but it is believed that in principle one can say that the randomness in statistical mechanics is due to ignorance. Okay, not intrinsic, not dynamic. Okay, not intrinsic seems to be more clear. Not intrinsic. Not intrinsic seems to be more clear than not dynamical. Not dynamical is less clear because we are not sure whether this is not dynamical, because there is dynamics involved in this. And so here one has to do more work and try to understand whether to establish that it is not dynamical, because you can have ignorance coming out of dynamical. So ignorance may be of dynamical origin. Okay, so because just like what happens in chaos, you will not know where the system goes, so you are ignorant of the final state of the system, but that is because there is a dynamical origin to that. Okay, so this part is something which is not as clear as it is in the case of so the stochastic. The point is that in statistical mechanics, or in systems like macroscopic systems, So the randomness is not coming because of the dynamical structure, but it is because of the collisions. The information is lost because of the collisions, and this information that is lost is continuously and irreversibly redistributing these particles such that the dynamical information is lost. And that is the reason why we are not able to understand that this is of a dynamical origin. But now you may ask a question, so, but collisions are also dynamically treated. Yes, collisions are dynamically treated, but there is an inherent indeterminism in terms of, for example, if a particle is colliding with the other particle, in which direction are they going to emerge, even though the collision is elastic, is uncertain. So you can only say that when you define scattering cross section, etc., it only talks about probability of the particle coming in this particular direction. So statistics enters through collisions, and the collision induced uncertainty, collision induced randomness into statistical mechanics. And so the ignorance is coming because of the collisions in statistical mechanics. And it is this ignorance that gives rise to temperature, that gives rise to entropy, and that gives rise to all the averaging that is required for the system to start from the microscopic dynamics to calculate the macroscopic properties. Okay, I think that's all that I have to say about this.
Yes, sir, that was very comprehensive. Thank you, sir. Sir, regarding this chaotic system again, I have another small doubt. In the case of problems like bifurcation problem, at certain growth rates, chaos emerges and it disappears after that a particular interval. Oh, why does it happen so? Or is it like you were saying that there is this time gap tau after which this chaos emerges? Is it like this growth rate for a particular growth rate, the tau is very small? Is it something like that?
No, not like that. See, the tau is on, see, if the system is exhibiting chaos, there are two things. So let's say I have a system, okay, and then there is some parameter of the system. Okay, so let's say I have a parameter. Okay, let's call this parameter to be some alpha. Now there is a system variable. Okay, that is system state variable. Let us call that as x. Now you are interested in asking what is x of t. Okay. Now this x of t, you can examine this x of t. Examine this x of t for different alpha. Okay, alpha could be some interaction parameter or some. It is some parameter of the system. Now for some alpha, okay, for some alpha, x of t is constant. That means x of t is constant for a given x of g. Okay, or for some alpha, now let's say I change alpha. Now x of t is periodic. So now what we say that as I am changing my alpha, the behavior of this x of t for all initial conditions. If it was constant earlier, whatever initial condition you give, it will remain there only. Then you say, okay, this is one dynamical character. Now, second, you go on changing your alpha. At some alpha, what happens? Instead of staying same thing, x of t now becomes periodic function of t. That means what? The nature of solution has changed. Then we say that from whatever value of alpha, this constant to periodic change is happening, we say there is a bifurcation. That means the nature of solutions has changed. Now, after some other alpha, this periodic can become doubly periodic or multiply periodic. So, whenever the nature is changing, we say that the bifurcation has taken place. Okay, so there is an interesting route to chaos. Suppose if you are taking this as your alpha, and then you say, okay, you are talking about x of t as for a very long t. Let's say initially there is only one particular point it will reach. After that, it has 2 points. That means it is going back and forth between these two. Then each of that will bifurcate into 2 points. Each of this will bifurcate into several points like this. So that means this 2 becomes 4, becomes 8, and so on. And then there will be a situation where you will see that there are infinitely many periods, and then it becomes chaotic. Okay, so this is a very famous route called period doubling route to chaos. Period doubling route to chaos. This is not the only route, but this is one of the interesting route to chaos. Okay, so there is so now what happens? Okay, the question that you are asking is, suppose if it is chaotic up to this between this alpha and this alpha, and for after some alpha, this may be again become periodic, possibly periodic, or it may become quasi-periodic. It is possible. So this is all a part of the dynamical behavior of this system with respect to this given parameter. Now, in a physical system, this given parameter might be related to some kind of an interaction of the system, or interaction within the system, or interaction of the system with the surroundings, whatever it is. Now, depending on those interactions, it is possible that the nature of the dynamics changes. Okay, so the dynamical systems can exhibit chaos. See, the system is always nonlinear, but it's not that nonlinearity implies chaos. Nonlinearity is necessary for chaos to happen, but it is not sufficient. So system can be simply a steady state, or it can be periodic, or it can be multiply periodic. In all those cases, we don't call it chaos. Okay, and chaos is a very complicated dynamical state where you have a complete it's look like randomness. Now, one can understand what this randomness is in the following sense. What happens when a bifurcation takes place? Okay, so let me just, even though this is a little bit digression, but since you asked this question, maybe it is. So let us use a very simple map. There's something called logistic map. Okay, so this is supposed to be a model of population dynamics. So let's say I have 4 alpha xn into 1 minus xn. This is an iterated system. So you give x0, you will get x1, you feed x1, you will get x2, and so on. So this is a map. Now this alpha is the parameter here. Okay, so this is the parameter. Okay. Now suppose if I take alpha to be some value less than 1 by 4. Okay, let's say I have alpha which is less than 1 by 4. Now, if alpha is less than 1 by 4, then what happens? So let me say that this is a map from interval 0, 1 to interval 0, 1. That means I will have 0 to 1 here and 0 to 1. And let me draw a 45-degree line like this. Okay, this is essentially y equal to x line. Now for alpha less than 1 by 4, this graph, if I plot, this graph looks like this. Okay, this graph looks like this. This is the graph of 4x into 1 minus. So this is x. And this line is y equal to. Now suppose I want to understand, suppose I take some initial condition. So let's say I take this as my initial condition. I want to know what will happen to the dynamics of this. So if this is x, what is y? Y is given by this. Correct? Now I have to give that as x next for the next iteration. So I go to y equal to x. Okay, this is y equal to x. So that is my next x. So this is my next y. Next x, next y, next x, next y. So you can see that I started with this initial condition and then I have gone to 0. So as x goes to so I have one initial condition like this. This is the trajectory. Okay. Now let me say that I will try to use another initial condition. Let's say somewhere here, close to 1. Okay. So this is my y. And where is my next one? Next x is I go back to this. And then again I go to 0. So you can see that for all initial conditions as n goes to infinity, xn goes to 0. This is basically a dynamical characterization of the system, because wherever you start, you will go to 0. Now I can say that x equal to 0 is an attractor. I can say this is an attractor because it is attracting all trajectories. Wherever you start, x equal to 0 only you will reach. Okay, so this is like it's an attractor. Okay, now what happens? Suppose if I assume that I am now going on changing my alpha. Now let's take a situation where this alpha is greater than 1 by 4. Okay, if alpha is greater than 1 by 4, let me carefully draw this. Okay, if alpha is greater than 1 by 4, then what happens? This one will actually be like this, because as alpha is changing, this will change, right? This, because remember the height at x equal to half is 1 by 2 and 1 by 2, 1 by 4, and 4 and 4 will cancel. So you have alpha. If alpha equal to 1 by 4, then this curve, the maximum will touch this line. And if alpha is more than 1 by 4, it will go above that. Okay, so that is the situation here. Now remember, earlier, this is again 0, 1, 0, 1. Earlier, when alpha is less than 1 by 4, wherever you start, whatever is your initial condition, you are always going to 0. Okay. So now we will start with some point which is very close to 0. Let's say we start with this point, which is very close to 0. Now this is your y, go to y equal to x. This is your y, go to y equal to x. This is your y, go to y equal to x. Y, go to y equal to x. That means even if you give an initial condition which is very close to 0, it is going to this point. Now you take any other condition. So any other initial condition. So let's say take some condition like this. So this is your y, and then this is your x, y, x. It is also going there. So if you look at this situation, for all initial condition, for all initial conditions except x equal to 0, as n goes to infinity, xn goes to some particular value, which I will call it as some x star. So this value, let me call it as some x star. So now what I can say? I say two things. I say that this xn or x is equal to x star is an attractor. Not only that, I also say that x equal to 0 is a repeller, because however close you start with that, it is going to be throwing the trajectory away from it. Okay, so we say repeller is like unstable and attractor is like stable. Okay, repeller is like unstable, attractor is like stable. Now what happens? See, earlier all the initial conditions are going to 0. Now all the initial conditions are going to this x star. Now do you think this is clear or not? Dynamically this is a difference. There are everything is going 0, now everything is going to this different point. So whenever there is a complete change of the dynamics for all initial conditions, then we say that there is a bifurcation. So from here to here, the nature of dynamics itself changes. Okay, so this is what we call. So we say that bifurcation occurs at alpha is equal to 1/4. At that point, bifurcation. Okay, so this is the nature of bifurcation. There is a lot of theory of there are books written on bifurcations. So the nature of bifurcations, and there are different names for bifurcations and so on. And so these bifurcations will continue. Okay, and it turns out that as alpha is increasing, this period, this will further become unstable. Then new stable points will come. Then unstable, stable, unstable, stable. And to tell you what happens in chaos. Okay, so chaos, when chaos happens, there is something called dense set of unstable periodic points. Okay, what do you mean by dense set of unstable periodic point? Suppose you have a space like this. Okay, when do you say it is dense set? You take a point and then consider any small neighborhood of that point. There will be one periodic point in that. That is, in every open set, around a point, in every open set around the point, however small it is, there exists an unstable periodic point. So what is the job of this periodic point? Just like this x equal to 0 is pushing the trajectory away from it, all the points are pushing the trajectory away from themselves. And there are infinitely many of them, there are densely many of them. As a result, the trajectory always gets pushed in much more violent fashion than a Brownian particle is pushed by the solvent molecules. This is the dynamical origin of the randomness in chaotic systems. Okay, I must tell you that one of the work which I did when I was a PhD student was try to find out these unstable periodic points of a system. Okay, and I was able to do it by a technique which is using statistics, and usually statistics and dynamics don't go well together, but I have used the concepts of statistics to find out the locations of these unstable periods. Because remember, finding the locations of these periodic orbits is very difficult, because if you are trying to go towards it, it will try to push you away from that. So it was very important to find the locations of these periodic orbits for many important things like controlling of chaos and synchronization and things like that. And one of the, I consider to be one of the interesting work, and I really enjoyed doing that, is to find the locations of these unstable periodic points in a system. And for that, I have used an interesting technique in statistics. So I had written a paper, one of the paper on this is chaos, order statistics, unstable periodic orbits, and chaos. So that is about the dynamical origin, how the randomness comes in chaotic system. Because there are dense set of unstable periodic orbits, the trajectory gets pushed or kicked away from each point, and as a result, you will see that there is a randomness. But remember, there is no randomness in the sense of collisions or anything. It is a dynamical structure that every periodic point becomes unstable, and hence trajectory gets kicked here and there from the location of each of these points. Okay, so I think we had drifted a little bit away, discussed certain things that are outside the syllabus. But anyway, it is good. I have also thought about these things after a long time. We don't really teach these things in syllabus, but some things, sometimes we have to recall, otherwise we will forget ourselves.
Yes, sir. Thank you, sir. Thank you for taking this deviation and explaining it, sir.
Yeah. Hope it was clear. And
yes, sir. It was very clear. I think at this point, I think I am starting to hurt my brain.
There is intrinsic mechanism which we are ignoring by virtue of which it seems inherent. Avinash, do you mean this with I'm sorry, I'm seeing only no. Maybe it was an old posting. Do you mean to say that it is with respect to quantum mechanics? Avinash? Okay. So there is intrinsic manner which we are ignoring by which of it seems inherent. Well, that is also true. That is also possible. But only thing is that if it is so, which is difficult to determine whether it is ignorance or if it is intrinsic. Because if it is ignorance, then we will be able to say in principle what all to do to get rid of our ignorance. Okay, suppose if I say that I don't understand statistical mechanics, but that is, I don't know much in statistical mechanics, but I can say that, okay, if I read this book, if I do these problems, I will understand. Okay, so we will be able to at least draw a kind of a blueprint of things that we can do to get rid of our ignorance. But practically, it may not be possible. Okay, then we can say, but if you are not able to draw any blueprint, or if you're not able to draw any algorithm by which we can, in principle, get rid of ignorance, then we have to believe that it is intrinsic. Yes, so if we are able to give Q and P for all particles, then the ignorance can be gotten rid of, right? So then perhaps there is no randomness, or you can also follow every particle and obtain what the randomness is. In simulations, yes, we do that in simulations. Okay, but in simulations we also have the difficulties with respect to this nonlinear. Okay, that is where these two things will. Okay, Ashwin is asking for more such discussions. Yes, I have no problem to have this kind of discussions, but this is our syllabus. Maybe we can complete the syllabus.
So, sir,